Good morning, everybody. Hello, hello. Am I coming in loud and clear? Let me know in that chat box. Can you hear me out there? Good morning, Jun Sheng. How are you, Carl? Meng Lu. Good morning, everybody. So, can you believe it? It's week 8. Week 8. Where has the time gone? Just a reminder, today at 12 noon, we will be doing a feedback session for the writing assignment if you want to come. Okay, they were very popular last week, and this is a way to get some feedback on your assignment. Good evening, Elena, or Elena. Sorry. Where are you? Let me know where it's evening. Are you in Europe or somewhere? Where are you? Canada. Oh, hello. Awesome. Um, well, today we're going to continue with integration. Integration is the final part of this course, and we're going to look at integration by substitution. So let's have a look. All right, so what we're going to concentrate on today is substitution. So it's like a strategy. Now, some of you might have seen this before. Let me know if you've seen this before in the chat. So integration by substitution. All right, Abdul Rahman, awesome. So we'll look at integration by substitution, and then we do something slightly different where we talk about integration of odd and even functions. Okay. So this is sort of this bit is different from this bit. Okay. But this is important still. Okay. So the idea with integration by substitution is to take a difficult integral or a challenging integral, and I'll show you some examples in a minute. And what you do is you make a substitution and what happens as a result is you get a much simpler integral. Okay? So it kind of takes something that's difficult, and through a substitution process, you end up with a simpler integral, which you can manage. All right? So it involves a substitution, as you would think. You get a simpler integral to appear, and sometimes you need to manage the limits of integration, but that's not for all problems. Okay? So let's have a look at how it works. So this is the idea down here. This is just some background information, and the basic idea is sort of captured here. Sometimes it is difficult to solve an integral, and what you try to do is simplify the problem, okay, through a change of variable or a substitution. Okay, so but this is the most important thing. Okay, so this is the integral that you start off with, and you can kind of see that you've got a function of a function and the derivative of this u function. Okay, here you're integrating with respect to x, and over here you're integrating with respect to u. So this is the more difficult form on the left, and over here is the simpler form. Okay, now you can also write this in the following way. You can also write this as something like this, right? F of u of x times the derivative du dx. Okay, so you can kind of see there, oh, the dx's cancel, and you can integrate this thing with respect to u. Okay. All right. So probably the hardest thing with this technique is the choosing what the substitution should be. But it's kind of like the chain rule. It's the integral version of the chain rule. All right. So let's see how this works with some examples, because I think the easiest way to learn how to solve and apply these integrals using a substitution is just to look at tons of problems. Okay, and hopefully you'll get the idea when you're looking at a particular problem. Okay, so let's have a look. All right, so the basic idea is here. You want to identify f and u. That's your substitution. Okay. And this is the derivative of the substitution. And these are all inside the integral. All right. Then you form a simpler integral and you integrate. So let's see how it works, like I said. Okay. The suspense is growing. All right. Solve the following integral via the substitution u equals this. Okay. So for this one, you're actually given the form of the substitution. Okay, you can see here 3x squared minus 5 is actually inside here. And if you look closely, the derivative of that is also here. So what we've got is something that looks a lot like this now, okay? Because, 6x is the derivative of this. You've got u to the power 4. Let's just make the substitution and do it, okay? So if this is my substitution, the derivative is going to be 6x. So I can find that there, and it's multiplying through. So this is a fine, a good substitution. All right. So let's call this I. So this is going to be u to the power 4. I'm going to move the du dx over here. Okay. And of course, these things cancel off. And now, instead of integrating this monster, where you would have to, expand the brackets and do things term by term, you're only integrating a simple power function. Okay, so that's that. That is this thing here. Okay, and it's a super easy integral to knock over. Okay, so if I integrate this, I'll get 1/5 u to the 5 plus a constant. Okay, and now I want to just go back to my original variable. Da, 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 da. That's it. Pretty easy, right? Pretty easy. Now, one of the things that made that problem easy was they told us the substitution. They said, let u equal this. That's not always the case, okay? Sometimes you'll get questions where you have to make a choice for u, okay? So that requires a bit more judgment, and but there is a strategy, right? There is a strategy. So for this one, if I wasn't given this, what I would look for is some part of the function where its derivative is being multiplied through by, okay? So you can see the derivative of 3x squared minus 5 is 6x. So that's a good substitution. Okay. You can try different substitutions as well. Okay, it doesn't have to be this one, but this works well for this particular example. So for those people who haven't seen this before, let me just pause and throw your questions into the chat. Is there any part of this example that you would like me to repeat or discuss a bit more? Let me know in the chat, people, because this is nice. It's not always the case though. Okay. So if there's anything else you'd like me to discuss about this problem, hit me up. Good question about the C, Maximilian. So this is not a definite integral, right? So this will work for all C's. When we get on to an example like, let me have a look, like this one, there won't be any constant or anything like that. Okay. So for this one, you don't like it works for all constant C, but if you have numbers in the integral sign, then that C will disappear. Does that make sense, Maximilian? Yeah, no worries. All right, let's have a look at another example here. Okay. Solve the following integral via a substitution, but oh no, they don't give you the substitution. Oh no. Oh no. Oh no, that's terrible. I'm outraged. Okay, so can anyone suggest what we might do for a substitution in this problem? So we want to identify u in some way where u dash is multiplying through. Who can tell me on the chat? If you're making a substitution here, what might you do? All right, Maximilian. U equals x cubed plus 1. Okay, well, that's a good starting point. This is almost the derivative of that, isn't it? So what we can do something sneaky. I like your substitution there. What we can do is go, aha. So what we can do is multiply through by a third and 3, and now that is exactly the derivative of that. How good is that? Okay, let me just go back to my big head. Yes. Okay, so you can manipulate integrals by multiplying and dividing by constants and stuff like that. Gets you what you want. Okay. So for this one, let's follow Maximilian's advice and let u equal x cubed plus 3. That way I'm multiplying through by the derivative. Okay. So let's call that I or something. All right. So let u equals x cubed plus 1. So the derivative is going to be 3x squared. So there's your 3x squared. There, that'll become cosine u, and that'll become du. All right. So by substitution, okay, I is going to become 1/3. 3x squared is just du dx. Cosine will become cosine u. Okay, these things cancel off. Goodbye, goodbye. So now you're integrating cosine u with respect to u. Nice. Okay, so that's going to become 1/3 sine u. And the last thing we want to do is get back to x's, okay, plus a constant. Okay, and so again, we had to make a choice there, and deciding what is appropriate is a strategy and a skill that you'll be expected to learn. The best advice that I can give is look for the derivative of this multiplying through somewhere else inside the integral. Okay? All right. So questions for that one. Let me know in the chat. The substitution wasn't given to you, but hopefully we can look at what we've got. We can form a connection between that part and that part. Now, sometimes substitutions don't work. Okay, you'll make a choice and then it'll go nowhere. Well, the strategy is go and choose a different substitution. So there can be more than one. Okay, and some of them will make it really simple. Some of them will make it more complicated. But that's where the skill and the strategy are. All right. Let's look at another one. Okay. So now it's getting a bit harder, people. Now it's getting a bit harder, especially at 2 a.m. where Abdul Rahman is. Okay. Solve the following integral via a substitution. Okay. So let's call this I for integral. All right. So let's look at this now. Can we form a relationship between one part of the integrand and another part of the integrand where you see the derivative? So what happens if I write it out like this? Oh, Abdul Rahman, even at 2 a.m., he's super sharp. Okay, if I write it out like this, okay, maybe you can see the relationship. So Abdul Rahman, why would you choose u equal natural log of x? It's a good choice, but can you justify your substitution at 2 a.m. in the morning?
I'm going to try talking, sir. Can you hear me?
Yeah, you can talk, man. Go for it. Good morning.
Good morning, sir. Because the derivative of natural log of x is 1 over x.
Exactly. Exactly. And Carl says the same thing. So you can see here, if that's going to be my u, I'm multiplying by its derivative right next door. Okay, so that's a great substitution. And Carl's also on the chat backing you up there, buddy. So good job. So let u equal natural log of x. So the derivative equals 1 on x. Okay. So by substitution, let's knock the integral over. All right, so if you use that, we'll get cos of u. And we've got 1 on x, which is du dx. They'll cancel. And now, oh my goodness, you're just integrating cosine with respect to u. How good is that? So there's the complicated situation. There's the simple situation. Okay. So sine u plus c. And let's get back to x's. Okay. So how good is that? So these were quite, hopefully the explanations are getting you thinking now. You look for part of the function where you multiply by the derivative, okay? Look for part of the function where you multiply by the derivative and let that equal u. That's a great starting point, okay? All right, so questions so far, people. Questions so far. Everybody can talk. If you want to turn your microphone on, there's only 43 people here. So if you want to ask something about these problems or you want to put something in the chat, now is the time to do it. I guess one good question is, how can I check my answer, right? How can I check my answer? Well, okay. So we want to differentiate this and show that it equals this, okay? So what strategy can I use to differentiate this problem here? Can anyone tell me in the chat or on the microphone, if you're differentiating this, what kind of rule would you use? Anyone? Anyone? If you're differentiating this, how would you do it? What? Yeah, Nicholas. All right. Booyah. Okay. The chain rule. Absolutely. So you want to, for that one, you would let, oh my goodness, u equal log x. Okay. Show that it's this. So hopefully now you can see the relationship between integrating by substitution and the chain rule. They both involve a substitution. Okay. They both involve a substitution. In this case, you're integrating. In this case, you're differentiating. So you're doing the opposite process. Okay? All right. Okay, so let's have a look. Let's have a look at a slightly more challenging one. Now, this is a little bit annoying because you could go, well, I could expand this bracket and then integrate, but I don't think I'm going to do that, okay? And if you look here, the derivative of this isn't sort of here anywhere. So this is a slightly different example that I'm going to show you, okay? So what I'm going to do, I'm going to aim to simplify this here, okay? And I'm going to say, okay, I'm going to let u equal x minus 1. Why? Because u to the power 5 is easy to integrate, but x minus 1 to the power 5 is not so easy. Okay? And so what happens with this remaining x? Well, you can get that in terms of u, right? So now what I can do, I can replace x minus 1 with u and x with u plus 1, and this actually simplifies greatly. So if you use that, du dx is going to be 1, okay? So you can just insert a 1 here if you want, all right? And the other thing is, let's manage these integral lower and upper limits of integration. Okay, so let's do that. If x equals 1, then, okay, so u equals x minus 1, so that lower limit is going to be 0. And if x equals 2, u is going to be, all right, it's going to be 2 minus 1 equals 1. All right, so by substitution, I is going to be the following. Well, we change limits of integration from 0 to 1. Oops, yep. X is going to become u plus 1. X minus 1 is going to become u to the power 5. And I've got that here. All right, so that's going to cancel. And now I'm just integrating this. This is easy to integrate. I just expand it twice and integrate. Okay. So u to the power 6 plus u to the power 5. There you go. That is a much simpler integral than expanding that. Okay, so let's do it. Okay, so I'm going to get 1/7 plus 1/6. Okay, if I simplify that, I get something like 13 on 42. Okay, so important point there, we appropriately manage the limits of integration. So this bit is new. Okay, because we really want just a number here. We don't want a function of x at the end or something like that. Okay. Also, note our substitution got rearranged. Okay, so you can see here that was our original substitution, and we moved it around to get x in terms of u, which took care of that part. Okay, so they're two slightly different things in this example that we didn't see in these examples. Okay, so this is a bit more difficult. So before I continue, any questions for that particular example? Okay, let me know in the chat, turn your microphones on, let me know what you're thinking, people. Let me know what you are thinking. All right. Okay, so let's look at one more. Now, it's asking you to solve this particular problem via a substitution. It's actually not necessary to do that. And so even if you're very comfortable with using the substitution technique, can anybody think of a way to solve this using other techniques, not using a substitution? So some of you may be thinking, oh, come on, Chris, it's 2:30 in the morning here. I'm very comfortable with integration by substitution. Well, if you are, try to think of a different way to solve this problem. Okay? Think of a different way to solve it. Okay, Abdul Rahman, quotient rule. Well, there isn't a quotient rule for integration, Abdul Rahman, unless you're integrating by parts, I guess. That would be one way to do it. But I'll show you an even simpler way to do that, not using a substitution. Anyway, let's do it using a substitution, and then we can talk about other ways. So based on our previous example, what might our substitution be here? Who can tell me or suggest something? What might u equal in this one? So this is I. 4 is an interesting idea, Russell, but when you differentiate 4, what do you get? You get 0, which isn't going to help you much, right? Because then you'd have to multiply by 0 somewhere. So x squared, Abdul Rahman, that might work as well. 4x. Yes, I think that might work. I think Aidan and Hira are closer with what I'm thinking. X plus 1, I think, is a good substitution to start with. Here we tried x minus 1 to simplify that mess. Here I think x plus 1 is a reasonable one. But there are many ways to solve these problems, okay? So don't worry, you might be able to use a different substitution. Okay, so let me just tie that off. All right, so if u equals x plus 1, the derivative is equal to 1. And we can rearrange that to get x equals u minus 1. Okay, so what I'll do is I'll put that one in the bottom and I'll put that one in the top. I think that's how I'm going to do it. Okay, let's also work with the limits of integration. So if x equals 0, u is going to equal 1. And if x equals 1, u is going to equal 2. Okay. So let's try to work this out, and we will see what we can achieve. So by substitution, okay. So we're going to be integrating from u equals 1 to u equals 2. 4 times x can be replaced with that. And x plus 1 squared can be replaced with that. Okay. So now all I'm going to do now is just to divide that into each part, and then we'll have two power functions which are easy to integrate. Okay. So u squared into u will go 1 on u times, and that into that will go that. Okay. So now this is the power function u to the minus 1. This is the power function u to the minus 2. So these are easy to integrate, hopefully. Okay. So this will become logarithm of u, and this will become plus 1 on u. Whoops. And we just want to evaluate that at u equals 2 and u equals 1. Okay, so it's going to be 4 times log 2 plus 1 on 2 minus log 1 plus 1 on 1. Okay, and now we just need to simplify that. That's going to be 0, right? A half minus 1 is going to be negative a half. So you're going to get something like this. Okay. Because it's a constant, Carl. Good question. Why can we factor the 4 out? Because it's a constant. Okay. So any integral, if you have an integral, right, and it's alpha times a function where alpha is a constant, it's alpha times the integral. Okay. If you don't want to factor the 4 out, you don't have to, but it's up to you. I just like to have it out the front because it simplifies. Otherwise, you need a 4 there and a 4 there, and does that kind of make sense, Carl? Cool. Nice. All right. So who can think of a different way of solving this problem? Now we're bringing out the morning discussion on integrals. Integration by parts, Naomi? Yeah, we haven't learnt that yet in this course, but that's definitely an option for this one. Okay, we will learn integration by parts. I'm thinking even simpler, people, even simpler than integration by parts. Even simpler. Oh, Dijat, I think you're on the right track here with the simplicity. We can make the numerator a multiple of the differentiation of the denominator. I think you're close here. Let me show you something, okay? But I'm loving the suggestions. What I'm going to do is I'm going to make that very similar to that. Okay, watch what I do. Okay, so what I've done, I've added 4 and I've taken 4 away and I've factored that. Can you see how that's going to divide into that now? And that's going to divide into that. So you can do it like this. Okay, that's going to be 4 logarithm x plus 1. That's going to be something. Okay, I'll take the 4 out. Okay, this is going to be something like that. Okay. So what we did here was we simplified the integrand first and then, got it to work. You could say, well, Chris, how did you go from here to here? And you could use integration by substitution, but I didn't. Okay. So that's the same. All right. So this is a slightly different way of doing it. But you can see that in this question, they've said, solve the following definite integral via a substitution. Okay. So I think this is the way they want you to do it. Okay. Last part of the lecture today, people. And this is quite a fun section. Odd and even functions. And when you're integrating over these sort of symmetric intervals. Okay, so this is super fun and it's super, super interesting and super easy. Okay, so let's say you have an odd function and you're integrating over, hang on, let me do that. Over an interval like this. So -1 to 1, -2 to 2, something like that. Okay. If you know that f's odd and you're integrating over this interval, you know that the integral is 0. Okay. Why? Well, let me give you a simple example of an odd function. The two areas cancel each other out. That's negative, that's positive, and they're the same. Okay? So if I'm integrating a function from here to here, and it's an odd function, the two integrals cancel out, the areas cancel out. Okay? That is such a quick way to do integrals. So for example, if I was doing something like this, 100 to -100, or -100 to 100 sine x dx, I don't need to calculate the integral of sine x and then evaluate it from here to here. It's just 0. Okay, why? Because sine is an odd function and this is a symmetric interval. Okay, that's pretty cool. So what about even functions? Well, that in this case, you're doubling the area. So you might have something like this, where there's your even function, and I want to integrate from here to here. Well, you just integrate from here to here and you double the area. Okay, so here I'm integrating from 0 to a, and I'm multiplying the result by 2. Why is that interesting? Because 0 is an easy number to work with, okay? Whereas this might not be so easy, like this one, for example. Okay, so for example, 100 cosine x, that's going to be 2 times that. Okay, it's not as simple as this one, but it's still simpler. Okay, it's simpler. Okay, so there's an odd function. You just remember, you just rotate your page 180 degrees. Do you get the same graph? With even functions, you get a reflection in the y-axis. Okay, so if you had a mirror there, you would reflect this. Okay. Well, so what? Who cares? Who cares about these things? Well, for me, the most interesting thing for these odd and even functions is you can save time doing the integrals. Okay, so let me give you an example. Explain why it is simple to evaluate this. Okay, so this is a difficult integral. You can't do it by substitution. I don't think you can anyway. If you can, I'll give you $100 if you can do this one, right? Aiden says that should those be continuous? What do you mean, Aiden? When you say continuous, are you talking about a continuous like integrand or something? Continuous function? Let me know. So I'm just putting something into Maple now. So square root x to the power 4. All right. Yeah, it is. It is an odd function. Okay, why? Well, let's go over to the different parts of the function. Okay, so let me go over to our old friend GeoGebra. Okay, sine x is an odd function. Okay, it's an odd function. X to the power 10 is an even function. So even times odd is an odd function. All right. And if I multiply by this, that's an even function. So the whole thing stays odd. Okay, so if I put this into GeoGebra, let me just see if I can do this. F times G all over H. Get rid of these things. Okay, so we're integrating between -1 and +1. And you can see, as Aiden and Nicholas have suggested, between -1 and 1, this is definitely an odd function. You can see it from the graph. Okay, so the area under here will cancel out the area under here. Okay. So what you can do now is write down the answer. Okay, so let's explain. 10 x to the power 10 is even. Sine x is odd. And root 1 plus x to the 4 is even. Okay? This product is odd. If you divide by an even function, odd divided by even is odd. Oops. Okay? We're integrating on a symmetric interval from -1 to +1. And so what we can do, we can just say, right, I don't need to do any calculations. All right? So let's call this I. That's it. So how good is that, people? How good is it? So if you want to, impress your friends, okay? Let's say you want to impress your friends, say, oh, I know integration. Come up with some crazy, crazy combinations of odd and even functions that give you an odd function, and then integrate it between, say, -1 and +1. Just write down the answer. That's pretty cool. So it's integration without working, or you don't need to actually find the antiderivative of that. Okay. So what do you think, people? What do you think? Is that cool or what? Is that cool or what? Let me ask. Oh, crypto, Alan, I'm sorry, buddy. Well, isn't crypto kind of mathematically related? What kind of stuff are they buying, Alan? What are they investing in? Dogecoin? Oh yeah. Dogecoin. Yeah, it's pretty cool, right? So even if you have a question like this, right? Let's say, I don't know, some sort of question, and they want you to do it a certain way, and you know that that is odd, and that's a symmetric interval. You actually know the answer, right? You actually know the answer. All right, folks. Well, how cool is that? That's a good way to finish, I think. I'll be here for a couple more minutes if you want to ask a question, but at 12 noon Sydney time, we are doing feedback on assignments. It will not be recorded. Last week, people went nuts. They wanted to share all their assignments with everybody and get some feedback. If that's you, come along at 12 noon. And thank you for coming today. And I will, Nicholas says, I think Aidan and I should split the $100. Well, try it. See if you can find an antiderivative of this monster. So maybe I'll see you at 12, but hang around if you want to ask a question now. Okay, everybody? So thank you. I hope you had a happy Halloween. And yeah, I'll see you a bit later. So hang around if you want to ask a question. All right. Thank you, Ai-Chen and Abdulaziz, Nathaniel, Maximilian, Naomi, Carl, Jordan, Meng Lu, CZ Chan. Thank you, Azur. Good job, Dijant. Thank you for coming. I know it's a long 2 hours. Okay, I hope to see you a bit later.